Ladies and gentlemen, it's a pleasure to be here. So it's an absolute pleasure to see everybody. I have to confess that it's been a few years since a PhD student has finished in the group, so I haven't had a pleasure to introduce somebody, so it's a special event in light of everything that's happened from COVID all the way to this point. Ron is a fantastic and the most pedagogical person I've ever met, probably. He's a rock star musician, if you don't know him, but you probably see him at some point on campus. But today he's not going to play guitar, although with you, I never know if you're going to do some surprise, so I wouldn't exactly be surprised if there was a surprise. With that said, Ron is a graduate of mechanical engineering from the faculty upstairs there. Was first in the RBNI Nanoscience and Nanotechnology program when I was the director of that program, and our paths joined, and he joined on board, and ever since has basically become a better expert at inhalation and drug delivery to the lungs than I am. So probably I'm the first person who's learned through the X years of research you've done. The time is for you to shine, so I'm going to step back and take them on the journey. All right?
Thank you, everybody, for coming. I'm very excited, I must say. I feel like the beginning of the semester, first lecture, it's very exciting for me. During my master degree, I delved into the fascinating world of electromagnetism. And I had also the privilege to be the student representative of the RBNI program. And as Josue said, that's the time our path crossed, because he was the head of the program. Through the end of my master, I found this TED Talk of Josue when he talked about drug delivery. And as someone that comes from a home that my mother has a master in physics and chemistry, hi mom, and my father ophthalmologist with an MD, it was natural to me to drawn into this world of medicine and science together. And when I come to visit Josue lab, I see this great passion like I do. And as I say, if you follow your passion, success will follow. So today I want to give you, in the short time, to have a glimpse to that passion. And without further ado, let's start with the motivation and the background. So when we're thinking about method of drug delivery, usually consider injection and maybe pills, but did you ever consider the lungs as a pathway for medicine? So let's talk about that, but for understanding the drug delivery through the lungs, we really need to understand what is the lung, how it looks like. So let's do a small recap. So in general, the lungs is just an upside down tree. You have the main stem, which branching out to the small branches until you get to the smallest unit of breathing, which is the leaf. So in a similar way to upside down tree, the lung look exactly the same. You have the main trachea, which split into the big bronchus, which split down to the small bronchioles, and in the end you have the small unit of breathing, which is the alveoli. Most of the lung is the alveoli, and in the alveoli happens something very special. There's a transition between CO2 and oxygen through the bloodstream, because as you see, the acinar region, this alveolar structure, is very close to the capillary. And if you want to count how many alveoli do we have, it's a ridiculous number, a lot of alveoli. And the most famous thing about the lungs is that the area of oxygen and blood is around the area of 100 meters square, a tennis field approximately, and the blood that with the interaction with the lungs is approximately 150 milliliter, a glass of wine that I would not resist at the moment. So let's talk about drug delivery into the lungs. So we have two different types of drug delivery when you consider the lungs. We can treat the lungs locally, disease that related into the lung. Instead of going all the way from other direction, we can deliver the medicine through an open door, the airways, and also this is a very rapid drug delivery method, just 4 seconds of inhalation approximately. But also we have a systemic approach if we use the lung as a portway to deliver stuff to the blood itself. And you can think about Afrezza. It's a new company that give inhaled insulin for diabetes people. And you have less degraded medicine because you don't need to go through the liver. And also it's highly dispersed from the lungs to the heart and to all the body. So everything until now sounds great. But you ask yourself, okay, where's the catch? Where's the limitation of this method? So let me share with you that. So you see on the vertical axis, it's the deposition fraction. How much particles land on the tissue of the airways, of the lungs. And here you can see the particle size, different kind of particles that can enter the lungs. And if you think about deposition, this is the deposition fraction, how much particle getting into the lungs. And here you can see the different particle size that we have. So if we're going to target the alveoli, you can see that this is the distribution of particles, of size of particles, and how much get into the alveoli. And you see it's not a lot. The maximum peak is at 50%. If we want to target the bronchioli, for example, asthma or COPD, you see that this is the curve, and most of the lungs get the position inside the upper airway. So that's the real picture. And you say, okay, Ron, it's not that bad because we can actually make these small sizes and then target the alveoli or the bronchioli to treat the lungs or a systemic delivery. Unfortunately, these sizes are not approachable in day-to-day inhalers. So actually the window of opportunity that we have is actually that big particles, and as you can see, the ratio and the efficiency of inhaler are very, very low. And for children, this is even worse. So what we can do about that, and that's what I want to share to you today. So you see this kid. This kid slide down the slider, but something really weird happened to his hair tips. So while the kid was sliding, he accumulated excessive amount of electrical charge, which we don't see in the day-to-day activities, but the hair tips is so thin. So the ratio between area to volume is so small that electrostatic play a significant role on the hair tips of the kid. And that brings me to talk about electrostatics in inhalation therapy. So when we think about an aerosol getting outside of inhaler, aerosol also very small, like the hair tips. And for that reason, they will be also very sensitive to this electrostatic effect. So where charge coming to the aerosol, in a similar way as the kid accumulates the charge, aerosol by triboelectricity takes some charge from the neutralized inhaler and only then deposit within the human body. So if we consider off-the-shelf inhalers, we know some of them accumulate big amount of charge. Nebulizer have several electrons. Dry powder inhalers have around 200 electrons. MDI, the most common one, can reach to 500 electrons. And in academic device, we can generate a very, very charged aerosols. So how does electrostatic charge affect the deposition? So when we consider the lungs through all its scales, if we're going to zoom into the interaction of the particle with a tissue, we're going to see something really interesting. The particle depolarize the tissue and then attract to it. And a key factor that I want you to remember during this lecture is you see the electrostatic force is inversely proportional to the distance. And for that reason, in the upper airway, I expect this force to be mild, but in a small region, the small compartment of the lungs, I expect this force to be very, very strong. And what's really surprised me when I look back in the literature is that most studies of electrostatics being done on the upper airway. For example, this computational fluid dynamics show what's happened to particle deposit within the upper airway when you enhance the charge. And also in this study, yeah, I know, the name of the research is Muhammad Ali. Maybe he have a 64-age crisis and decided to investigate the electrostatic. But in this in vitro model, they exposed the upper airway into some charged particle, and they see increasing the position by triple the amount. So let's, and we also saw in our lab a really interesting phenomenon. I want you to see how Donald Duck being kidnapped outside of the stage. So something very similar happened with the electrostatic. Here you can see an in vitro model of a cavity, and you see the particle being close to the tissue and suddenly being kidnapped into the wall of the alveoli. So we know that we need to understand what does electrostatic do, and we're asking ourselves if in the deep region of the lungs they play a very significant role. So let's dive into the scary equation, Newton's second law, and try to understand what is the dynamic of a charged aerosol. And unfortunately, when you add the electrostatic force, the equation becomes non-linear and hard to solve, but don't worry. We have an alternative. We can use non-dimensional analysis, which present big numbers, and each number presents a phenomena for the position. And if one of the numbers is significantly larger than the other, we can confidently say that this is the main reason for the deposition. So we have the Stokes number, which tells us how hard it is for the big particle to take the sharp turns of the lengths. And we also know the inverse Paclet number, which tells us that due to random motion of the air molecule, particle can deposit on the tissue. We have H, which we call for heaviness, and this is for heavy particles that are free fall into the tissue. But last and not least, we have the induced charge effect, the electrostatic mechanism. And a key parameter I want you to see, that all of these terms depend on the characteristic length and also the velocity. And what's really unique and challenging about the lungs, that the lung is a multi-scale problem, which means the length always changing as deeper as you go into the lungs, and the velocity decrease because every split you need to distribute the air to more and more generations. So we talked about it, that in the upper airway there were studies, and to be more confident about what's going to happen in the small airways, I decided to do this non-dimensional analysis. So here you can see many different kind of inhalers and their charge expected, and on the vertical axis you can see the particle size. So I ran this to figure out who is the most dominant non-dimensional number. And of course, from the heavy particles, we see that gravitational sedimentation taking place. For the small particles, as expected, diffusion would play a role, but merely amount of 20 electrons, and that's it. Electrostatic governed the position within the acinar region. So that made me curious, and I said, okay, does electrostatics affect the position in the deep region of the lungs? Let's see it. Let's validate the theory that we have. So let's take me to our next step, which is acinar, to build an alveoli model. And as you know, models by definition are not perfect, yet some of them are useful. So the model I'm going to share with you today is that model. I'm going to explain to you why I designed it that way and what the result that I got for the acinar region. So what were the challenges in fabricating that model? First of all, I want it to be in anatomical scales. We're talking about the short distances that we want from the wall. We want to account for real anatomical distances. And we want to have a respiratory flow. We want electrical conductivity as we have on the tissue. And last but not least, we would like to have transparency so we can see inside what's going on. So before that, I want to ask you a question. Is the Earth flat? Of course, the Earth is not flat, but why it took us so much time to realize that is because day-to-day objects are significantly lower than the radius of the Earth. And something very similar happened to an aerosol inside the alveoli. The aerosol diameter is very small compared to the big diameter of the alveoli. And it means that when the alveoli, when the aerosol fly above the alveoli, he cannot tell that this is a cavity. It's too big for him to realize that. So the particles see just an edge. So I want to take this idea while I'm designing my model, and I'm not the first one to do it. So here you see this group, they design a cylinder which have these edges, and they reach a cavity flow that mimic the acinar region. So I want to take advantage of that idea. So I took a glass, and I diced the glass with trenches that are gonna do to me a 2D cavities in my region of interest. And it looks like this under the microscope. And you see I got the real scale of the lung, around several hundred microns for a cavity. And to account for the electrostatic conductivity, I use the atomic layer deposition and deposit ITO on the model. So then I have the conductivity and the model, and now I need to take care of the flow. How can I get a reciprocatory flow? So I designed this microchannel. I'm gonna share with you this plane, y equals 0. So in this plane, this cross-section, I designed using PDMS and 3D printed cast this part. And this part, mainly what it does, it feeding with a high velocity air, get rid of the high velocity, and give us a very slow velocity using a syringe pump. And I wanted to see here what the profile that we got. We see a very slow velocity and a very small Reynolds. And this is exactly what we expect when we're talking about the deeper generation of the lung. You see, Reynolds is the number that tells us how much dynamic pressure we have versus the viscosity effect that we have, the shear stresses. And I here compare the Reynolds. You can see that in the upper side of the lungs, you have a very high Reynolds, which means you have a chaotic flow, a very turbulent flow, but then the flow, because of the air being transmitted to more and more generation, Reynolds become very low and even get under 1, which means we entering a zone of creeping flow, very slow velocity. So how this affect the alveoli? If we're gonna zoom into one cavity, we see that the flow is shearing the flow within the cavity, and we have this vortex effect. We have a separated flow, and this is exactly what we aim for when we compare ourselves to other studies that have been studying the velocity and the velocity profile inside the alveoli. So now, after designing the model and building the model, I want to share with you how we exposure to particles. So to take care of the size, I use aerosol generator and 2 consecutive dryers. And I use polystyrene particle because they have similar charge under this mechanism. As in a control group, I use a neutralizer. And then I expose them to my model, and under the microscope, I can see the deposition pattern. So let's share some pictures. So this is a single alveolus. So each sphere is a particle that landed on the model, on the in vitro models. And here you can see all my 6 alveoli separated by their diameter. And you can see the different height of the particle using the color code. So you see a lot of red particles. I'm going to get into it in a second. So let's try to understand the results. So we started to exposure the model with 1.1 micron, which known to be a very heavy particle in the acinar region, which would deposit by gravitational force. So this is the upper view. We see the particle landing like a raindrops on the model. If we're going to flip side and look at from the side, we can count how many particles we have in each cavity on the septa, and we see homogeneous distribution like a raindrop, as we saw. Now let's expose the same particles, but let's charge them with approximately 100 electrons. And then we see something completely different. We see that the septa got almost all the particles, while the cavity stays empty. So charge increased the septal deposition for that particular case. Let's talk about how we can interrupt this result and get to a more sophisticated and a broad understanding of the position in the acinar. So if you consider our model, the septa was very big. It was 50 micrometers compared to the real septa, which approximately 12. So instead of calculating the position fraction, we can normalize by the area and calculate the concentration of each case. And then we can compare the concentration on the septa versus the concentration on the alveoli inside the cavities for 3 different sizes. One that governed by gravitation, one that governed by diffusion, and one in the middle that more convective and doesn't relate to any of the mechanism. So we see for the heavy particles that from 10 times more particles on the septa, we got to almost 50. And we see that half of micron double the numbers on the septa, and for the small particle, the diffusive particle, we see inverse effect. We see that now electrostatic guide the particles to stay inside the cavity and don't diffuse outside. And this graph shocked me, because when I travel around the world to many conferences, all the people that talking about drug delivery put so much focus on the particle size of their inhalers. And of course, it's important. Look at all the gray histogram that's increasing. But look what's happened when there's no regulation about the electrostatic charge. If there's no regulation about the electrostatic charge, all the results shrink to the same value, approximately 50 times more particle on the septa. So electrostatic effect should really be encountered. And a very interesting phenomenon that we saw, against my intuition, I must say, that when we look at the cavity in the alveoli, we saw a very interesting phenomenon. In the entrance to the cavity, where I expected to see most of the particle, I actually saw a depletion of particle. And when I started to count the particle on the septa, I see that all the particles are there. So a lot of particles attracted to the corner shape of the septa, and we hypothesized that maybe it's because of the curvature of the septa that more charge accumulate on these corners. But of course, this is we hypothesized that, and this needs further investigation. So great. We talked at the upper airway being vastly investigated. We talked about the acinar region, but what's happened in between? So for that, we encountered the bronchioles. So we designed that model with Moran and Leo from our lab. You see, we have here a 3 generation of the lung, the generation 11, 12, and 13, because this generation related to a lot of disease taking place in the lungs. And we're going to see this cross-section. And I want to tell you before that, sorry, not cross-section, this plane, but I want to tell you before that the cross-section we use for our model are square. And a lot of people think that it should be circular, but apparently in the lung, it's deeper as you go, it's more arbitrary shape. So it was more convenient to us to present a square cross-section to look at the microscope more easily. So the design of the model is very similar to the previous one, using a PDMS, and with the syringe pump we control the flow, and we have Poiseuille flow as usually have in this region of the lungs. And remember this Carey equation, the particle dynamics one? So we managed to solve it numerically. So I want to show you what we expect the deposition to be inside this model. So here you have the height where we're going to release the particles. And on the horizontal axis, you're going to see which generation this particle get to. So we see that most of the particles that we expose exit the model. They don't want to interact with the model. They have the best chances to deposit in the end of the model because they have more time to fall down. But when we expose in the simulation the same particle in the charge case, we saw something completely different. All the particles from the same height deposit along the generation of the model. You see this straight line that we talked at the beginning? This is the electrostatic force that kidnaps the particle from a certain distance into the tissue. And we want to validate that through the experiment. So you see, in a neutralized case, we see the chances increase as you're getting out of the model, the last generation. And for the charge case, you see similar deposition along the model. We want to take this idea one step farther. And now I want to talk about what's happening in a disease situation. For example, obstructive disease. A classical one is COPD, which is the third reason for death in the Western world, or asthma. So what usually happens is, under these circumstances, the tissue becomes inflamed and become thicker and thicker, and also there's a lot of secretion of mucus. And that results in a very, very narrow airway. So what is the result of having some of your airways very, very narrow? If we're going to think about that as a flow and a circuit, we can think about the airway as a resistor and the lung as a potential difference of pressure. So you have a flow, and the resistance of the airway is highly dependent on the diameter. And as the diameter dramatically decreases, the resistance increases significantly. And for that reason, no flow want to go into the sick places. And I remind you that the flow is where the medicine is, because when you inhale it, it's fly along with the airflow. So that's the reason this is the third leading reason for death in the Western world, because you cannot treat them. All the medicine go to the healthy places, not to the sick places. So what we're looking for is kind of a Robin Hood, that can steal from the rich airways and give it to the poor one, the small ones. So I thought about that maybe electrostatic can play a role there, because electrostatic effect becomes stronger when the velocity is small, and also when the distances are small. For that reason, I hypothesized that electrostatic can play a significant role in these obstructive diseases. So we designed that model, which have a normal path and constricted path. And I compared the different ratio between how strong the electrostatic versus the gravitational force along the model, the generation of the model. As you see, the more you constrict the airway, the more sick it is, the electrostatic become more significant. But be careful, because when you make it constrict, there's less flow into it, so less medicine. So no matter what sophisticated mechanism of deposition of particles do you have, if you don't have flow, you cannot play. So you need to be careful in designing that model for that perspective. So we designed that model. So you can see that we have the main channel that feed the system. We have this pipe that get rid of the high velocity. And here we have this split, generation 12, that split the flow between the normal size versus the sick one, the constricted size. So as you can see, we just took 30% constriction on our airway, and the result was that if we feed the model with approximately 2.5 milliliters per minute, 80% of the flow would go to the normal, and only merely 20% of the flow would go to the constricted region. The plan is to count the particles that we have in the constricted size, compare it to the normal size, and see if we have any change in the ratio between the numbers. And I'm sorry to disappointing you, but I cannot share the result yet. We're counting them at the moment, but I can share with you some of the simulation we talked before. So here you see a particle fly around 40 microns above the surface, and here you can see the top view of the same particle. So now we split the simulation into two different simulations. The same particle continued to the normal size, and the same particle continued to the constricted size. And we suddenly see that on the generation 14, the particle deposit versus the other particle that just escaped the model. So we kind of found our Robin Hood, because now a lot of particles can escape the healthy tissue but stay in the constricted one. So that was my question of my PhD. Yes, electrostatic play a significant role in the deep region of the lungs. But that led me to another question. Something very interesting occurred to me. So when we think about electrostatic effect, there's a kind of a debate in the literature between, okay, electrostatic is an added mechanism, which means it's increased the position. So maybe you're going to lose all the particles at the beginning of the lungs and nothing will left to the end of the lungs. So you continue to research what's happening in the deep, but maybe there's a problem and no electrostatic would stay, and nobody answered this question. So we want to encounter how deep the electrostatic particles can reach. And the reason nobody answered this question, it's really hard to build a lung model. The lung is very complex. You see, this is the cast of a human lungs. On the right side, you have the blood vessels. And to build a model that also have the upper airway, the mid airways, the end of the lung, the deep region, it's very complicated. The best method to use is a gamma scintigraphy, but this is very, very expensive. You cannot do this experiment on children. So you cannot count on this method for everybody. It's not that accessible. So the golden standard is the cascading factor. The cascading factor is just a filter system that tells you what is the size of your particles. And building on the size, they can tell you where the particle going to deposit in a real lungs. But of course, this very simplifies the situation. You see, there's no taking care of the electrostatic effect, humidity, the different geometry of the lungs. So we need something else. So another approach is to use simulation. The problem with simulation are very, very expensive, both in money and both in time. And also there is something very limiting in simulation, because you give the simulation the equation. So you want always to have a two-way street, that sometimes the reality going to tell you something different from your theory. So this can be a very good a validation of what you're doing, but it's not, you cannot always count on the simulation. But something that we can say about simulation, that some of them are really, really smart. They find very different methods how to get away from hard computations. So I want to present to you the trumpet model. So what is the trumpet model? It's a very simple and genius idea. So if you consider a bell of a trumpet, which increases in size, it can mimic the upper airway. And as you go along the generation, you can mimic the different splits of the lung, because this approach gives you the same volume and also the same flow. You have an average velocity that's approximately the same in each region. So, for example, this simulation started with the normal airway, and then in the end, where it's become complex and really small scale, they present their trumpet model. So I want to take this idea, so I designed a new model, and this model have the acinar region as a trumpet model. So I actually improved my previous acinar model, my alveoli model, by introducing it to a changing velocity, which mimic not one generation or two generation, but a series of a few generations into the acinar. And another cool method that I must show you is the one-path method. The one-path method is trick the particles. When a particle gets to a junction in the lung, a split in the lungs, you have two options: to continue the simulation or live out, and we're going to account for the particle that live later on. So the idea is that the particle doesn't know which door is which. So you have a statistically distribution, so what particles will do, and you can account only for the particles that continue into the lung, and then you save yourself for the exponential growth of the lungs. So this is what we did. We did this one-path model, me, Daniel, and Nadia. So you can see this is the inlet of generation 3. Then you continue to generation 4, and then you have the real generation 5, but also the exit. This is the real one, and the one to the right is the exit. The challenge with designing this kind of model is that when you do it via simulation, you just put the boundary condition on the computer software. But in the real life, you need to make this boundary condition real. So how you design these exits so accurately? So we match the resistance of the acinar with the last exit, and then we construct what is the total resistance that we have at each point of the model. So some of them connected in parallel and some of them connected in series, and we got to this formula. To build the resistors that we needed under this value, we found out that the length should be very, very long, and we don't have a place on the model. And we would not want to change the diameter because we want the particle to enter the junction and see a mirror image of the two splits, of the splits. So we thought about this idea, so maybe we can change only the end. So using basic calculus, we calculate what should be the resistance of the trapezius kind of airway, and then we can calculate each exit using this formula, which just depended on the geometry feature of our design. And to validate that, we use simulation, CFD. Thank you, Tirosh, for helping to validate simulations. So we see the velocity, and we compare ourselves to the previous studies, and we see that we aiming and getting similar result of Poiseuille flow and the same magnitude of velocity, and also regard the cross section. So they took a circular one while we take a square one, but again the lung shape is arbitrary, and this is just to give us an idea what's going on inside the lung. Also, it's important to say that our model is a planar model and not going in all the different direction versus gravity, but it still can help us understand different phenomena of electrostatics. So we made it. We built this model for real. So you can see here generation 3, the different exits, and it ends in the acinar region, the alveoli generation 19. And to validate the results of the CFD and both of our theoretical calculation, we use a similarity check. We expose the model to water, making similarity between the Reynolds. We can see that flow split homogeneously. How we did it, we put water and particles inside the model, and we know the exposure time of the camera. We know how long each picture took, and we can look for the fastest particles and measure their distance. And distance versus time give us their average velocity, and then we can continue to the other side of the split and compare the velocity of the particle over there. So we made it. We have a flow rate that split approximately 50% with the 10% error, and it's okay because the lung is not perfect either. So the split also doesn't account for perfect 50 and 50. And here you can see an exposure setup and a deposition of particle, each generation being exposed to a half of a micron particles, and we can count them and realize how the particle distributed along the model. So here you can see the different generation of our model. Here you can see the deposition fraction, and here we have two cases, half of micron particle, charged versus neutralized. We see few interesting things here. First of all, we see that a lot of deposition occur in the inlet of our model, and we also see that some of the particle reach to the acinar region. Here you can see a zoom into the acinar, and you can see also that the half micron particles want to escape the model. They're very convective particle, which means not governed by gravitation and not diffusion. So that's what we expect to see. We see that the electrostatic effect, as an additive mechanism, deposit at the beginning and increase the deposition on the cost of the particle that would like to reach the deep generation of the lungs. But don't confuse, this is a one path. What's happened when we think about multipath? A lot of generation, because in my model I have only 2 generation 4, right? But in a real situation, as you increase, the number of generation increase as well. So if we take the single path that we have and multiply each generation by the numbers of generation we expect to have, we can get this picture of the deposition. And we see for half of micron, we see that from 82% when they got charged, they decreased to 45%. So we see dramatically effect of electrostatic charge on the deposition. And our next phase is to investigate what would happen for a different kind of particles with a different velocity of inhalation. For example, what would happen for a particle very heavy? Did it would succeed to get to the end of the lung with electrostatic, and how it would change the deposition there. So I want to give you my take-home message. So, you know, our lung is a very sophisticated device. It learns how to deal with the different particles that we have in the air, and we like it that way. Because if somebody, like yesterday was Yom Ha'atzmaut, so everybody may grilled, and there's a lot of smoke in there, and we don't want to breathe it. So our lung designed in a very sophisticated way to protect us. So the lung is, in evolutionary perspective, protect us is a filter for different sizes. And this is a huge drawback when we want actually to breathe the aerosols, to inhale them as a medicine. However, when we think about electrostatic charge, this mechanism is not familiar to the body. So if we put a lot of charge, maybe there's a window of opportunity that we can use in order to change the way drug delivery being done till today. So thank you very much for your precious time. And I want to thank my wonderful, wonderful group. And that's it. If you have questions, I will be happy to answer them.
Thank you so much, Ron. Always very entertaining. I'm like, oh yeah, thank you for explaining this and that. And what did I do for 4 years, really? So do we have questions from the audience?
So regarding the constricted regions model, what makes the particles go to the constricted part and not to the deeper regions of other pathways?
Okay, so as we talked about that, so you have the flow that splits. For example, you have the 100%, and the 100% prefer to go to the healthy airway. In our example, we saw 80% versus 20. So medicine go with the airflow. They follow the airflow. So most of the medicine is moving into the healthy part. So the chances for deposition is higher. That's all it says. So also the unhealthy part get a position, as long as it's not too constricted, and then the chances are almost zero. So the electrostatic effect enjoy the phenomena of the tissue become closer. The distance is what play the major role. Compared to the other mechanism, gravitational or diffusion, which also enjoy the distance and the small velocity, the electrostatic effect enjoy it more because it have the square on the denominator. So for that reason, it's more favorable for electrostatic than the other mechanisms.
First of all, very nice presentation, very nice simulation, very nice videos. I have one comment, a lot of questions. First of all, the comment, you say that you were amazed that the particle actually deposit on the septa.
Versus, yeah.
Actually, this is a very good proof of the effect of the electrostatic, right? Because if you have a surface with equal potential, most of the charge in the surface will be in the region of the sharp edge. So actually, the fact that it's going to sharp edges or very sharp curvature, it's support the idea. Now, a couple of questions. You put a lot on emphasis of the electrostatic, and you suggest that the charge particle actually induce the polarization of the tissue. Can you a little bit elaborate about the effect actually of the polarization of the tissue? Because you have here the water, you have the epithelial cells,
and the mucus, and yeah.
And in disease, it will be changed because of the water actually affect negatively. How you calculate or imagine this depolarization? What is
occur? Yeah.
And what is the size of this depolarization? And how it changes in various physiological condition?
This is a great question. I'm going to repeat it a little bit. So how you can be sure that you have this conductivity effect inside the lungs on the tissue? Because the tissue it's a jungle. You have the mucus, you have proteins there, you have sugars there, many stuff there. And sadly, I must say, there has been no investigation truly from the perspective of an aerosol that interact with the tissue itself. There's a lot of in vivo experiments that match with the theory, but in the literature, they most attribute to the tissue as properties of water. And from the water properties, you can relate to the image charge that occur. And I agree with you, there need to be more robust study about it. We talked about it, an experiment that could be really interesting is to take a tissue and using a conductive AFM to approach it and to realize what is the force supply on the particle to validate exactly what you said. But this is a dark realm of this field. You hit it, yeah.
I think it's a massive question mark.
Definitely. Good question.
Anybody? Nobody. Okay. Well, you're not yet a doctor, but you're
Not yet,
there.
yeah.
So
Check on one thing, yeah.
Thank you very much for coming in numbers. We appreciate it. Wish you all a wonderful day. Thank you, Ron, for a wonderful